Um, Good morning, everyone. Can you see the screen?
Yes, sir.
Okay. Um, this will be a series of three lectures on galaxies and galaxy dynamics. Um, it's not like sort of um, easy to compress all of that into these three lectures because that will be too much. So what you will get is basically through these lectures a set of sort of basic understanding of the way we understand galaxies, and try to see what are the kind of questions right now that we are trying to address in this subject, and to move ahead. Basically we like to do see what is the current research also going on in this area. So I made a very brief outline of today's talk, more or less. So today what I'm going to talk is about the structural properties of galaxies, like the galaxies, the general composition, the classification. Um, then we talk about a bit of the spiral galaxies and the elliptical galaxies, and try to understand how we can understand galaxies from a physics point of view, and see that how do you basically uh, um, address galaxy as a many body system. Okay, so before I go into the galaxies in general, and the general introduction to the galaxies, I am going to show you these beautiful pictures of Hubble deep field. And this is, as you know, that the Hubble made an extraordinary contribution to our understanding of the how galaxies are formed. Okay, this is the only instrument which can take images of the very early universe. Okay, this is the only space telescope available, with all the capabilities that we need to know. So it looked into the southern part of the sky in the Fornax dwarf region, and as you can see by the cross mark here, and it created a beautiful part of the sky. Apparently there were it's a blank field. So the deep field often means the part of the area of the sky which is generally less bright, with not a lot of bright stars in that. And then you take an image and then integrate for long hours of time, and then you create these beautiful images. And often this has created the one can see the galaxies through these images at the very early stages of the formation. Okay, so that's the Hubble deep field, and this is where there are some images from this the Hubble telescopes, the IR camera and the NICMOS, and you can see how the redshift 7 galaxies are. Okay, so I hopefully you all know what is redshift, so I'm not going to spend the time on that. And so the redshift 7 means almost when the universe was a few hundred million years old, like 650 here. And you can see the galaxies. We often even with the HST we cannot resolve these galaxies to very large extent. So we almost often see the more or less like a point sources uh, to a good extent. And then this is at redshift 7, so which as we see 650 million years old, just after the Big Bang. And then you have the farthest image of a galaxy, the Hubble series, which is the redshift 11.5. Okay, which is almost at the dawn of the almost at the beginning of the reionization era of our universe. The universe has gone through a set of phase transitions, and reionization is one of such phase that had started around the redshift like 10 plus, and then redshift 11.1 is where you see the farthest known galaxy. And these galaxies are it's very disturbing to see, basically, because you don't see any particular spectacular images that you are used to see in the nearby sky. So this is basically a galaxy, but it seems like when you analyze this galaxy, it already seems to be an evolved galaxy, which is a bit strange. And the mass is 1/100 of a Milky Way mass. Okay, this is the galaxy at 11.5. You can look at the details from the Pascal's paper 2016. Okay, so now this is how the galaxies are at the very early universe. But of course, if I start talking about these galaxies, this is not very impressive. So as I said, the galaxies in the local universe are really, really different, and we need to understand them. So the way we try to understand this whole subject of the galaxies and the galaxy dynamics is that you get to know maximum, or the maximum possible way, the local galaxies, because the local galaxies, the maximum amount of details in that. Okay, so if you know all the details in the local galaxies, so you are basically equipped to say, okay, these are the galaxies of the nearby universe, the universe which is close to us right now. And then once we understand the properties of the galaxies, the physical properties of the galaxies, their mass, their size, their color, their stellar populations, there are the number of other properties, then you say, okay, we can go back to in the past or in the very early universe, and try to see how we understand these galaxies. Okay? So with this view, I will get into the sort of the local universe, and this is what a picture of our galaxy on the right hand corner. You see that this is a image of the Milky Way, but this is not a real one. This is artistic impression, and this is basically shows that the galaxies that you see in the local universe, like for example our Milky Way, is totally different. And then, as you can see, in the center there is a elongated structure which is in the yellow color, and then you have spiral arms, and then right from the center of the galaxy, so I can't show the cursor, right from the center of the galaxy, at 8.5 kiloparsec down, you have our sun, okay, which is moving with a 220 kilometer per second around the galaxy through these parallels. Okay? So the major composition of the galaxy that you see in this Milky Way are actually the stars of the galaxy. Okay? The stars are the major contribution in terms of a visible mass. Okay, visible mass. And then next to stars, there are of course gas, which is cold hydrogen gas, then the cold molecular gas. Okay, and then there are of course the other exotic objects in some sense, there are globular clusters, there are high velocity clouds, there are many different components exist in different forms. And even in the gas, when I say the cold hydrogen gas, there is also warm neutral hydrogen gas. So the galaxy, but for you to basically get a glimpse of the understanding, because then it's you can say that the typically the stars contribute to the 90% of the total mass budget. Okay, and then the gas is about 10%. Okay, but if we talk about the dark matter, for example, the galaxies are also we know that from a number of indirect evidences that the galaxies are not just the baryonic matter, but not just the stars and the gas, but this is also surrounded by some kind of spheroidal distributions of the dark matter halo. Okay, the dark matter halo, we're not going to. This is only indirect evidence to the gravitational, the force, so we don't have a sort of the direct evidence yet. Okay, So I think that's the typical like the way of the galaxies are like the, the compositions. And then as you like go from different galaxies, these compositions like the changes. For example, if you go to elliptical galaxies, the it is mostly the stars, okay, and then the very little like coal gas in it, okay. That will come to know like if we like move ahead in the lecture, so will get to know. So the elliptical galaxies and the spiral galaxies, as you can see, the Milky Way is a like prototype spiral galaxy. The difference is in the gas fraction, okay. This is one difference, but the one difference is in the gas fractions. It's typically the coal gas. Okay, the elliptical galaxies are often devoid of the coal gas, and the spiral galaxies are actually there is a lot of coal gas. And there are some spiral galaxies, for example, typically the low surface brightness galaxies are like actually dominated by the gas, more or less. Like there are the galaxies where there are more than 50% of the mass budget is into the neutral hydrogen gas. So that's the typical like the compositions of the galaxies. And then if you look at the galaxies, then you see the different shape and sizes. Okay, the typical size. So what I show here in the middle is the disky spiral galaxy, and then on the right you have an elliptical galaxy, and on the left you have you have an irregular galaxy. Okay, so the typical size, if you look at the size, how do you determine the size? The size where you can see, like by your eyes, you can say, okay, this is the sky on the right hand side, you can say, and this is the elliptical galaxy. And then wherever the light goes, okay, wherever the light ends, sort of typically you would say naively, like, no, that's the size. Okay, so if you consider that, like, the idea is basically the size of the galaxy is determined by, in some sense, like where the stars end, basically where there is no more stars. Okay. So the naively, like, no, you could say that the stellar disk or the disk of the spiral galaxy are about few tens of kiloparsec. For example, Milky Way size is about 15 kiloparsec. The elliptical galaxy have a size of like probably to 100 parsec to the 100 kiloparsec. Okay, 100 kiloparsec size of elliptical galaxy would be like the massive elliptical galaxy. Often they are like in terms of stellar mass, they are also like pretty high. And these are called the CD galaxies, which reside in the center of galaxy clusters, the big galaxy clusters. And then these are like massive, like mass 10 to the 13 solar mass. Okay, the solar mass, and then 10 to this is the 10 to the 13 times the mass of the sun. And then you have a Milky Way stellar disk, which is 10 to the 10 solar mass. There are some dwarf galaxies, which are 10 to the 7 solar mass. And then we have also a peculiar galaxies, like which are the ultra faint dwarf galaxies, like about visible mass is just 1,000 solar mass. So what you see in all these is the dynamical range. Dynamical range, in a sense that the lowest to the highest is like huge difference. So it's like from ultra faint dwarfs to the city galaxies, there is a 10 to the 10. Okay, 10 to the 10 orders of like basically 10 orders of magnitude, like difference, like in the masses. And also the size is also, you can see like the 0.1 kiloparsec to, so sorry, 0.1 kiloparsec to 100 kiloparsec. This is also like quite a range. Okay, so this is a very challenging thing. Reason I said mention all this in a very general, or not going into the particular details of the galaxies, is that these are huge dynamical range. This dynamical range is not easy to model theoretically, and that's very challenging. Okay, even from the simulation point of view. Okay, the people who try to like do cosmological and body simulation, the full scale cosmological. So they have like the hard time to like produce like this variety of like the masses in the image. So this is like open for you to also explore in future if you wish to, because that is where the this is a very active area and it's kind of challenging. Okay. Now, when I say that this is the elliptical and the disk is spiral galaxies and irregular, obviously you can see like different types. So basically that is like one important thing. So I wanted to like put a picture of the Hubble-Divaculus diagram, and in the Hubble-Divaculus diagram, like it seems that the elliptical galaxy is on the right side along a line of the sort of a tuning fork, but it's no longer the tuning fork. But on the upper right arm, you will see that the spiral galaxies, okay, without the central elongated structure, which is called the bar, and then on the left hand, sorry, on the bottom arm, you see the spiral galaxies with a bar. So this is the barred spiral galaxies, these are spiral galaxies, and then you have intermediate spiral galaxies. Okay, now and then the junction of this, like the two, the spiral on the right side and the elliptical on the left side, or you have a lenticular galaxy, the H0s. You can see H0A and H0B. Okay, now and then on the far right, you will see the irregular galaxies. Okay, this is a very instructive like the diagram, because moment you see the sky and take an image, there will be like thousands, depending on where you like look in the sky, there can be like thousands of galaxies, and depending on how you like what kind of exposure, what kind of distance. So if you take a deep images, you will see like maybe thousands to millions of galaxies in a very small field of view, and you will see like lots of galaxies. The question is like, you may ask like this, say how many of them are spiral, how many of them are elliptical, okay, how many of them are barred spiral, how many of them this thing. So like this classification is an important state. It's important state because we want to know how first of all we want to know that like what is the fraction of this, the elliptical versus the spiral to the barred spiral. What are the fractions of the galaxies? Which galaxies are dominating in a given area of the sky? Or are there you have a grip on like this classification scheme, then you can also like address the bigger issue, like how these galaxies are formed in a sense. So because then you don't take a galaxy, how a galaxy formed, but how a class of galaxies are formed. Okay, so this class is important, and that's why people in the 1930s because you may think, or it may be actually true, that the elliptical galaxies may be forming differently than the spiral galaxy because they look different. Okay? They look very different. So, and then the barred spiral galaxy and the spiral galaxy, maybe there are like connections. Now you can also like join probably the vertical lines on the right hand side connecting from spirals to intermediate spirals to barred spirals. Like, are there like connection in this? Okay, so that's the essence is basically the classification. Without the classifications, you will not be able to answer the right questions. So that gives you like sort of the pathway to do that. Okay, not only so then I'll come to that. So now if you look like this is the Galaxy Zoo, and they are doing an excellent job because this become a citizen science projects in UK, and they have done like sort of classification of galaxies very, very pictorially, okay? And in a sense that like common people can take part in this, and you have a spare time, you look into the part of the like set of galaxies given in the in a in an archive, and you say, okay, I look at the image, I say, okay, is this galaxy from the irregular shape? Okay, so I can classify it accordingly, and then so okay, so 1, 2, 3, 4 like that, so you classify accordingly, and then so how the spiral arms are, like, are they open or are they tightly wound? Okay, so this is basically the way to like classify. Okay, so there are various, you can look through this diagram. If any questions, I'll be very happy to like answer. Not everything is like the transparent, but the essence is that like there is a lot of activity in classifying these galaxies, because the numbers that we are dealing with is like billions of galaxies, okay, in the archive. So one cannot just go into like one, it's not one person job, it's not 100 people job, it's like a massive, like you need to be uh, manpower required for doing this classification job, because there are various things into it, because the people also trying to do it from the machine learning point of view. Okay, so because you cannot, since you cannot handle this like huge amount of data volume, so they started doing in the machine learning way. But then there are other set of people who believes in like the classification by eye. So we want to know actually by eye, is this galaxy actually like have a two-arm spiral or one-arm spiral? Okay, is this round or a needle like? Okay, so we want to know by by eye. Okay, so not, so there is a like, this is a like, this is just a flow chart, and for the classifications, but I already like told you like why we want to do classification. And but not only that, so if you look at now, the galaxies are, the classifications are much more like complex. So this is the Spitzer image, so from Spitzer Space Telescope, and you can see that Hubble Divacular's diagram has also become more complicated, okay, because of the introduction of various types of spirals, various types of galaxies. Remember, our discovery, the scope is keep increasing because of the increasing power of the telescope. So we can look deep in the sky, we can look much more detailed, so lots of things coming up, so it become much more complex. So then the other question that comes out, the why you want to do classifications, as I said, like for example, typically question that been asked, like, okay, now you see a Hubble tuning fork diagram on the top, okay, uh, what was it at 6 billion years ago, for example? Okay, so there is still like the Hubble tuning fork diagram, but what you see from now to the 6 billion years ago is that the number of galaxies within the irregular is like much more. Okay, much more. I do not know yet that whether the galaxies from the irregular shape actually gone into the becoming the spiral, because that connection has not been made well yet. Okay, so we don't have a so this is basically the saying, other words, that in the early universe the peculiar shape was much more, which is probably believable, because the images that I showed you, the redshift 7, redshift 11, or maybe you can search by yourself also, even at redshift 2, okay, that you don't have like well developed spiral arms in the past, and then like the most round shaped elliptical galaxies actually. So there are actually the irregular fraction is much more, much more. So in other words, like maybe at the very early universe you only know. But then the question is basically that, because the irregular shape, you may think also that what if we are not able to see in details? Because at the very early universe, we don't have the telescope power to resolve. Okay, we resolve like a few kpc kiloparsec size actually. So which may contain the full galaxy, okay, within your resolving power of the telescope. So how do you know the details of the galaxy? But then I think it is more and more believed that like actually the galaxies, there are indeed probably more peculiar. There is no well-defined spiral arms, and it is actually uh, the irregular, actually irregular, because um, with HST, you can still like the look at galaxies at redshift 1, redshift 2 in a good detail, but not maybe beyond. But you can still see like the galaxies having sort of just forming like a spiral, or like this kind of features will be seen. So that makes you like believe that maybe the galaxies in the early universe had this born as a peculiar shape, because and then basically like move into like the more regular shape when they had enough time to settle down. So there is something called the settling down of galaxies. Okay, when a galaxy is formed in the early universe, there may be in a process. The physical process are much more violent. Okay, so there is a lot of like violent changes happen in the galaxies. Then as they settle now, and then sort of after they settle down, and then they have time to like sort of relax in some sense. Okay, so when I say violent, the phases, because in the early universe maybe the two galaxies will have like the probability of merging will be much more, for example. And then when two galaxies merge, their potential will change very rapidly and with time. So and that basically brings you the violent phase of the changes in the galaxy. So there is the obviously now you could say that look, like I want to like go back 8 billion years ago, 10 billion years ago. Okay, like what was it? Okay, so this is a challenging, and that's where you want to know also classification. Okay, all right. So enough of the classifications, a few images of the local galaxies so that you are familiar with. So we talked about the Milky Way on the left hand side, the Milky Way bar spiral galaxy. So like Milky Way, there are about 60% of these galaxies are actually bar, okay, which means having an elongated structure at the center. Okay, apart from the spiral, with or without spiral, it's possible. Then the galaxies you can see like on the right hand corner I show. So I don't have a cursor, but I can't see. You can see like a one elongated structure with a very diffuse light, and then you can see like there is also a in the very inner part there is some kind of a elongated structure. So this is called the nested bar galaxies, which are like bar inside the bar, and then they can be understood from their surface brightness profile, which will just come to now. Like what is that? So the surface brightness profile and the electricity profile. So one can actually fit ellipses to these images, and you will see in the inner part the ellipse will be elongated, and then there will be like changes phases, and then the phase angle, and and this is how the phase angle is varying. For example, inner part is like flat, and then it's going, and the on top is a flat, and then you can like determine the ellipticity of these galaxies. Ellipticity is nothing but 1 minus minor axis by the major axis, and then you can see the ellipticity is also going through like sort of peaks. So in the inner part they will peak once, and the outer part they will peak another time. So this is a typical like sort of the nuclear bar, and it's kind of very important ingredient to bring gas from outside to inside. Okay. So if you want to like for example ignite the central black hole, the black hole like activity, you need the gas to flow in. But to gas flow in, the gas must lose angular momentum, and this nuclear bar is the one such entity which can like do this job. Okay. There are also like the galaxies which are like very different when you look at a different orientation. The same spiral galaxy may look different, okay, depending on the orientation. And then there are galaxies which have like the central structures, which is like on the upper right corner, NGC 5746. You will see there is a box-like structures, and then on the right hand side is a Higgs and compare group. There's a structure is like more of like a X you can connect, and then there are also galaxies which are like a needle line, like as if there is no central structure. So the idea is basically to give you the kind of variety that we know, and it is the complex thing that like if you want to address their formation pictures, if you want to know their dynamics, okay. So this is the kind of like thing, like are they formed just like that, okay. So what is the difference between the needle like galaxy and the galaxy with the box like structure at the center? So obviously you can say, okay, the center is like different, but why? What happened to this? Like, how come some galaxies are like this and some are like this and that? So this is the kind of like the question that like puzzles us. Okay. All right. So then I think enough with the images. Okay. And now I want to take you through some kind of it like the measurements, because so far what we are talking about is that we talked about the classification. Okay, we talked about the how different galaxies are, okay? Different galaxies. And then this is of course so far too. You're talking about the stars. Okay, now you say, okay, so enough. So what can you do? Just like it's not about just looking, soothing your eyes. So let's what science we can do with that. So apart from the classifications, we can do like few measurements. Remember, the galaxies are in the sky, not in your laboratory. So we have like a severe limitation. So the only thing that actually you can measure from a galaxy is light and nothing else. The light, the distribution of the light. Okay, that's the only thing measured. So what we measure at a telescope is the flux from a given part of the sky. Sorry, the given part of the galaxy. So that is what we can measure. So the flux is basically luminosity divided by 4 pi d square. D is your distance, and then the L is the luminosity that is the galaxy is emitting. Okay, we can define a surface brightness, which is like the flux divided by the solid angle subtended by the small delta r in this, and one can show that the surface brightness for local galaxies is basically L by 4 pi delta r square. Delta r is like that area, so it is independent of distance. Okay, which means if you look at the surface brightness, at the different galaxies, the surface brightness don't change. Of course, there are limitations. The limitation is like at some point the distance becomes important from us to the object. So if you have the distant sky, for example, a redshift which is like bit higher, then one can talk about this I is going to 1 over 1 plus z to the power 4. So this is called the surface brightness dimming with the redshift. So that's a bit like higher level. So I think if you need only like we can talk about it, but I think right now we are pretty good that we can measure the surface brightness profile. So which means that we can actually talk about the distribution of the light within the galaxy as a function of r from the center of C. Okay, so that's what basically when you take an image on a CCD, you can actually like create a distribution of the light within your CCD with the pixels, and you can like basically you create an image of the galaxy and you measure the surface brightness profile. So the surface brightness is one quantity, and it's like the variation with the radial variation. At some in a complex structure, this can also depend on the azimuthal angle. For example, spiral galaxy, you can have r, and r as a function of r and phi. So I as a function of r and phi. So there can be, for example, the spiral galaxy, or the galaxies with the bar spiral, things like that. So there can be the surface brightness profile can depend on the azimuthal angle as well. Apart from this surface brightness profile, you have another useful quantity called the apparent magnitude. So the apparent magnitude is minus 2.5 log of the total integrated light that you do. So you can say, imagine like at a given wavelength, okay, either in the optical, which is going from the 4,000 angstrom to all the way up to like 8,000, 9,000 angstrom. In this band, you can like collect light. So like there are various ways to basically measure this, like the light distribution. I am not going to actually talk into detail about how you can do the measurements, because that will like deviate quite a bit from here. So just to give you an idea, only that in astronomy observations, there are various filters available. The filters which block other light but they allow only light. So there are some kind of band pass filters. For example, you can have a band pass filters in 4,000 angstrom to 5,500, which is called the G band, for example. Or for example, in R band, which is like around 6,000 angstrom. Okay, so centered around that. So you can have like, for example, the band pass filter in, for example, UV. Okay, of course, it's not possible from the ground, but for example, UV can go from 1300 to like 1800, which is a far ultraviolet, or maybe 2000 to 3000, which is like the near ultraviolet. Okay, for example, our own satellite AstroSat has like two such like facility for observing in UV from space. And then there are like the HST has like within this optical and all the way to like IR, like the infrared, which is like about 1.6 micron. So there are like about more than like 10 filters, such band pass filters are available. So idea is that you can actually like choose one of this filter, which is I define as a function of lambda here in this equation, and you can collect all the light within that and then make an image of the galaxy in that particular band pass. And then you say, okay, now I can like integrate all the light within this image and take the logarithm of that minus 2.5, and then this is the formula that you use, and the C lambda is some kind of a reference point. Okay, so when you measure the amount of light, you say you get some like X amount of light, but you say, okay, so how do I compare this? Is this bright? Is it faint? What is it? So you need a reference star, for example. Okay, so you say, okay, my galaxy is fainter than this many magnitudes compared to this reference. Okay, so that is the way to like do the apparent magnitude calculation. So once you have this apparent magnitude calculation, so that's a very useful quantity, because like stars, you can say, okay, this star is minus 6 magnitude. My galaxy is like typically, let's say 10 magnitude, 15 magnitudes, like depending on the bands, of course. But one can talk about this. So higher this number m, so the m can go from a typical galaxy like 14, 15 magnitudes in optical, and it can go all the way up to like the very faint. Okay, so larger the number, fainter it is in this notation. Then so the surface brightness, then the apparent magnitudes, and then once you have this magnitude determined in different pass band or band pass, you can actually take the difference of this magnitude and call something called color of the difference. Okay, the color is defined by the difference between these two magnitudes taken at a lambda 1 and taken at a lambda 2, which is two different wavelengths. For example, you can have one in the near UV, for example, like 2000 angstrom to 3000 angstrom, like let's say lambda 1, and another is, for example, let's say in the G band, for example, which is like 4000 to 5000 angstrom. So you have a two adjacent pass bands, and then you say, okay, I want to know the color of the galaxy. I'll tell you a bit like what we do with the colors and things like that if I have a bit more time. So let's go move ahead. So when we measure the surface brightness profile for an elliptical galaxy, and this is what is been plotted on the right hand side plot, which is the surface brightness, which is in magnitude per arc second square, and this is the logarithm of r. You can see that the profile is a very well defined profile, and as noted by Devacoders, this profile can be modeled. You can feed the profile with this function. This function is called the Devacoders profile, and this is this well fed actually. So it seems the most bright elliptical galaxies, then if they are not interacting with other elliptical galaxies, they always have this Devacoders profile. Okay, amazing, pretty amazing. Of course, the scenario can be different when you go to the fainter elliptical galaxy. Then, if you look at the spiral galaxy, then also you can determine the surface brightness profile. Okay, the surface brightness profile in the outer part, you can see the surface brightness profile. Remember, the surface brightness profile is almost like a straight line, and at the center it rises sharply. So the outer part, when the surface brightness profile is like a straight line or like monotonically falling with the radius, okay, that part is called the disk of the spiral galaxy. Disk of the spiral galaxy, and this is well fed by exponential. For example, if you take the logarithm of this id of r, it will be like minus r here, isn't it? And then it's basically log r versus r, it will be minus r with the slope of the rd, 1 over rd, right? Rd is the scale length here, the scale length with which the rate at which is falling. All right. So in the center, of course, like is like bit different. So we'll talk about it. So it seems like the when you model this like the spiral galaxies with the exponential profile, it has two parameters. One is the central surface brightness I naught, and the scale length, which is RD. This you can actually, as I said, directly measure from observation. Now this I naught is the central surface brightness, and depending on what is the value of I naught, is like the tells you like what are the different galaxies are. So in some sense, if you look at the center of the galaxy, there is a bright spot there. You can imagine the surface brightness would be much higher, which is true. Which is true. That's why surface brightness at the center is increasing, and outside it is falling exponentially. Exponentially. So this central surface brightness, if you take a distribution of this is the luminosity or the function for of the galaxies, and you see with the mu naught, which is the I naught, it's the logarithm of that. And then initially in the 70s, we used to know that most of the bright spiral galaxies have central surface brightness, which is around 21.5 magnitude per arc second square. Okay. But now of the discovery of the many fainter galaxies, which I marked by the red here, red circle ellipse, you see this is no longer true. There are lots of like low surface brightness galaxies. In other words, we have actually now discovered, because of the massive like the power of the telescope, we can dig down deep in the sky, and we can actually like see the fainter galaxies. And the fainter and fainter galaxies, they are very interesting in a sense that they no longer follow sort of like the Freeman's law of surface, which is in the 1970s, is completely changed, and there are much more fainter. But then you can of course like keep asking these questions: how fainter a galaxy can be? What is the limit? Is there a limit? Like when the galaxies were like formed, like who decides like the how faint the galaxy would be, right? What is the deciding parameters? These are some of the like very the questions that we don't know how to answer. Okay, so that's why I try to give you an example. And then the more and more the telescope power will come up, we will go towards this fainter side, because all the bright ones are taken already. So we don't have a much chance there, because HSTs, there are many big like the facility, telescope facility, which have already like done a spectacular job on the bright side. Okay, and so what is left is basically for you to dig down. Okay, so it's just like the fainter ones. So the bulges, so at the center, remember, like I talked about this, like the center part of the spiral galaxies, where the surface brightness profile like rises very sharply. Those are actually the bulge of the spiral galaxy. The bulge of the spiral galaxies are also like having a similar profile. This is called the Sarsik profile. If you have noticed or remember, the Bn was 7.676 and 1 over n was 1.1 over n equals to 4 in the case of the Irregular. So this profile is nothing but the Irregular's profile with n equals to 4. Okay, so it turns out that the spiral galaxies at the center host these bulges. These bulges, in many cases, they are like elliptical galaxies. Okay, but from the point of view of the light distribution, the surface brightness distribution. Okay, skip this, and just to give you an idea that like this is our local group of galaxies, the three main. Okay, the Andromeda, and then the M33, the triangular galaxy, and in the bottom there is this is the Milky Way. Okay, all these galaxies have very different central structure. All these are spiral galaxies. Andromeda, M33, and then our Milky Way, these are all spiral galaxy. But if you look at the central structures, they're all different. Just to give you a feeling, like what is this is our own neighborhood. So in our own neighborhood, the galaxies are like pretty much different in the central structure, but all galaxies have exponential. The M33, for example, it doesn't have any bulge at the center that we showed. So then you will remember that I showed you galaxies which are needle-like. So the needle-like galaxies don't have bulge. M33 doesn't have bulge. We see in face on, okay, in a different orientation. And then a question asks, how come? Why is that this galaxy could not form a bulge, or like was there anything that prevented it from forming bulge? So these are kind of like, if you know these things, they are directly related to how these galaxies are formed. One has to answer this question. Okay. So coming back to like the color a little bit, if you look at the suppose you have a like millions of galaxies, okay, and you determine their color. Like in this case, this is U minus R. This R is R band centered around 6,000 something angstrom, and then U band is around 3,000 to 4,000, and no, sorry. This is 3,600 to like 4,000 something. That's the U band, and you say that U minus R color, and then you plot as a function of the absolute magnitude. Okay, on the right hand side is the high luminosity, there's a low luminosity, and then bottom is blue, and then it's red. Okay, the U minus R color is like the more and more it is like towards like the lower values. It means the galaxies are bluer. This is like higher values. It's like redder. So it seems if you plot galaxies onto this kind of thing, there are galaxies which form the red sequence, the galaxies which form the blue cloud, okay, and then there are like intermediate stuff. So which means that the color magnitude diagram is a powerful diagram to actually segregate galaxies depending on what are the dominant source of light. I will not say evolution yet, because there are many things one needs to understand. But this gives you an idea. For example, red sequence is dominated by the early type galaxy, the elliptical, the S0 galaxy, which are on the left side of the Hubble diagram. The blue cloud is dominated by the spiral galaxies, more or less. Okay, and then the green valley includes some kind of a early type is those or like the again the this is not very clear like what is the dominant composition of the green body. Just to give you an idea, this is what basically the pictures from the Galaxy Zoo people. This is again the U minus R color, and you can see the lower value around 1 means it's a blue, and then the higher value 2 point something is red. Okay, so the you can see the galaxy colors in U minus R have two peak, one peaking around 1 point something and another peak around 2 point something, 2.5 plus. Okay, so which means that there is a bimodal distribution. Bimodal distribution, which means if you cut across along this, you will get two peaks. Remember, these contours are actually density contours of the galaxies. So you take the galaxy on this mass plane, U minus R versus the stellar mass of them. So you have a two-dimensional plane. In the two-dimensional plane, you have a number of galaxies, so you can actually make a density map out of it. So this is the density contours. The highest density are the two places, okay, around 1 and around 2.5 plus. Okay, and you can see that this gives you like very nicely an idea about how the stellar mass, as the stellar mass increases, how the color like changes. So it is seen that most of the early type galaxies, the elliptical as well, they are typically generally massive galaxies. This is the stellar mass, by the way. So around like 10 to the 5, 10, the 10.5 is 10 to the power 10.5, which means around 3 into 10 to the 10 solar mass. So 10 to the 11 is the 11 solar mass. You can see like the most early type galaxies are massive and red, and the late type galaxies, the spirals are like blue and low mass. Okay, so that's the kind of the essence of the color. And then there are lots and lots of like the studies that goes on. Like, did the galaxy from the blue cloud move to the red? If they did they go vertically? Did they go via something? All kinds of trajectories you can like do, which is has to have some physics in it. So the question is like, did the blue cloud move to the red frequency? In other words, the spiral galaxy moved to the early type galaxy. That's the question. Okay. All right. So we talked finished about the distribution of the stars and distribution of the surface brightness distribution, the magnitude, and the color of the galaxies from the stars. But then galaxies are, as I said, like not only like stars, there are gas. So on the left hand side, I show a plot from Barton and Gordon from 1978, where, and then Clemens 1988, you see the distribution of the H2. H2 means molecular hydrogen, and then H1 means neutral hydrogen. So neutral hydrogen, if you see, is like more or less flat with the surface density. The y-axis is the surface density, x-axis is the radius from the center of the Milky Way. Okay, and then 8.5 is where mark the sun. In the sun, the density of the hydrogen gas, the neutral hydrogen gas, is more or less flat. Okay, this is the state of our knowledge at 1988. Now, which is like 2008, you can see from Peter Carviller, there is a distribution of the hydrogen gas. It's going all the way up to 35 kiloparsecs or even 40 kiloparsecs. Okay, you know where the distance of our like LMC SMC is around 50 kiloparsec. Okay, it's almost touching there. So our Milky Way is like all the way going there, and you can see that the hydrogen gas is extended much more than the stellar disk. Stellar disk ends at 15 kiloparsec for the Milky Way, isn't it? And then you have a huge amount of neutral hydrogen gas disk going around. And then there are plenty of them. Okay, plenty of them. Plenty of galaxies, spiral galaxies have, for example, in this, I show the NGC 71744. You can see in the black, there's a stellar disk. And the contours are actually the hydrogen gas, which means that typically the hydrogen gas extends a factor of 2 to 3 times the stellar disk, which is like huge. So that's the kind of like the distribution of the hydrogen gas in galaxies. Okay, and people try to make a lot of effort. What is the the distribution of the hydrogen gas? So you can see all kinds of surface brightness profile. All this is from Bigel and Blitz 2012. So it's not very clear. It's not very clear. You may find something which is not actually exponential, and but people try to say, okay, gas distribution may be exponential. Okay, and that's not the all. But having neutral hydrogen gas is apart from this higher distribution, this is here a very important discovery, and this is the discovery about the dark matter in the galaxy. If you can see this galaxy, NGC 3198, where the stellar distribution surface brightness profile ends around 15 kiloparsec, and then the one can actually measure from 21 centimeter line, okay, the rotation velocity of the this hydrogen gas. So in the rotation velocity of the hydrogen gas, which is moving far away from the stellar disk, so whose potential under which influence it is rotating? You can see that the spiral galaxy, the circular velocity is flat all the way up to 30 kiloparsec, whereas the stellar disk ending almost at the 15 kiloparsec. So it means that that if you try to support this rotation velocity, the circular velocity, the stars and gas together is not enough. You need some kind of a missing or invisible mass of something that will hold or support to say, okay, velocity. Remember, v square is equal to gm over r. So you need more mass to have higher VC. Okay, very very naively say. Okay, and the fact that the VC square is equal to constant, you can say that the mass is proportional to r. Mass within r is proportional to r, which means it gives you a density structure which is 1 over r square. Okay, m is r square. So that's the kind of a dark matter halo profile in a galaxy observationally. So it's the pseudo isothermal dark matter halo. Okay, or having a core as I showed in the plot, the density versus the radius. But then people have done also the structure formation, okay, and they find that the dark matter in body simulation are no longer the core, but they have some kind of a cusp, which is 1 over r. So that 1 over r, it goes the infinity, density goes to infinity. So there is this cusp core issue which is not yet resolved. So this is the kind of a dark matter. and and then the spiral galaxies. So now you measure the two things. I'll come back to this plot later. But to give you an idea, that the spiral galaxies in general are rotationally supported. So the majority of the stars are in rotational motion. Very few in random motion. The elliptical galaxies, on the other hand, lack systematic rotation. They are mostly by the random motion. Okay, so this is basically the doctor of the spiral galaxy, but I'll talk tomorrow into a bit more detail about how we know this. Okay, from what we know that there is kind of thing. So these are on the just to give you an idea that the Vmax over sigma is actually the maximum systematic velocity divided by the velocity dispersion of the stars and versus the ellipticity of the object. For example, when we look at a elliptical galaxy, you can actually fit an ellipse to it, to the light profile. Okay, what you see in the image. And then we say minor axis, and then you can major axis. So ellipticity is basically 1 minus b by a. Okay, b is the minor axis. Axis. Okay, so the higher the value, the flattened it is. Lower the value, rounder it is. So that's the kind of thing, and it shows the how the kinematics or the motion of the stars are. Okay, so but anyway, there's this the galaxies, as I said, they have the massive. So we can find out the number of stars in the Milky Way from a simple understanding by the nearest neighbor stars, which is around 1.3 parsec away, and compute the density of the stars. Then we know the size. We can do a cylindrical volume of the Milky Way, for example, which is this. And then if you multiply by density, you get a massive amount of stars, which is 10 to the 11 stars in the Milky Way, which is a lot. So then I think we need to understand, if you want to go theoretical understanding, then the question comes, how are these 11, 10 to the 11 or the 100 billion stars are moving in the galaxy? Okay, are they like colliding? And so give you a very quick, this thing is that if you look at the gas in your room, there the mean free path is like much short, okay, shorter than the size of the the room. In other words, like the most of the galaxies, like they will collide, like when they move even at a few angstrom. Okay, so the gas in the room is very highly collisional. But on the other hand, the stars in the Milky Way do the same calculation, mean free path comes to be like a very high, and this is a knife. Okay, don't take it like say, okay, there are like many issues there. But what we can say that the stars never do head-on collision with another star in our galaxy. Even a Milky Way and Andromeda, in the future, if they collide, we will not know, because the chances that like the one will collide head-on with the other is like very low. I think I'll stop here because it's 11, and if there is any question, I will I'll take that up. Hello. Hello.
Yes, Kanak, you can ask them to raise hands and unmute, and they can ask the questions.
Okay. What are different? How do I say raise hands? Are they listening to me?
Yes.
Okay. You can ask questions if you have any questions.
So if you have the question, just raise your hand. We'll unmute it and then you ask the question. Okay.
Hello, sir. Good morning. Sir, am I audible?
Yes, please.
Oh, thank you, sir. So actually, the question is, in case of galaxies, there are certain kind of jets which have there's a certain kind of jets which come out from the central bulge of the galaxies. So in certain kind of galaxies, in certain types of galaxies. So my question is, are those jets a characteristic property of all types of galaxies? Like they are a property of both spiral and elliptical galaxies, or are they significant to a particular type of galaxy? Like, are they form only from the elliptical galaxies and not from the spiral ones? Is it so?
Sorry, I think there was a connection issue. I heard your first part that the some galaxies have jets. Is that the coming out of the bulge you said, right?
Yeah, right.
What is the question actually?
Oh, my question is that are those galaxies like those jets? Sorry, just a minute, sir. Sorry. Yeah, those jets which come out from the central bulge of those galaxies, are they significant to all types of galaxies? Like they are a characteristic property of both spiral and elliptical and all the other type of galaxies, or are they a characteristic of a particular set of galaxies? Like they are characteristic of only elliptical galaxies or of only spiral galaxies? Is it so? Hello. Hello, sir.
Hello, Kanak. Hello, Kanak. We can't hear you. Hello, Kanak. So I guess he has just disconnected. He will be back in the few minutes. Just be hold.
Okay, sir.
Hello.
Hello, Kanak. Can
Yes,
you? Yeah.
I can hear, but he seems to be online. I think he's got disconnected completely.
No, now he is on the mute. I will just unmute him.
Sure, sure, please.
Hello,
Yeah.
sir. Am I audible this time?
Yes, yes. So just a moment. So what I was saying is that the jet activity is connected to the supermassive black hole that resides in the center of the galaxy. Hello.
Okay.
So it means that and this depends. The jet can be like depend. So now it comes to the question is like, there are some jets which are like very large in like, in size. There are some which are small. Okay, so the jet from a galaxy is completely related to the supermassive the activity of the supermassive black hole. So there is nothing like a particular galaxy, but definitely, as I said, like the spiral galaxy can also have like a massive jet, like the large jets, but often many jet activities are actually in the elliptical galaxy because they have a massive black hole.
So those elliptical galaxies are more familiar to those supermassive black holes in the center.
Because the 10 to the 9 solar mass black hole can only be there in the elliptical galaxies, and you have like rare cases of when 10 to the 9 solar mass black hole are there in the spiral galaxy, and sometimes you may hear like there are the jet activity in the spiral galaxies, and in this case often the black hole has been like very massive. Okay, typical mass of a supermassive black hole in spiral galaxies are around 1 million solar mass, few million solar mass. Okay, so I think it's related to a lot like that, and then I think the jet activity is to do with the activity within the central part of the galaxy.
Okay, sir. Thank you, sir.
Santosh. Hello.
I just open your chat window. So there is a question from the Nisha and Pooja.
Okay, where is the chat window?
You just go to the bottom of your Zoom. There you can see the chat icon.
Okay, I saw, but I see only like one question, which is Suprabha Mukhopadhyay.
Okay, I will just read out the question. So just one sec. I will.
Why is that, Santosh? I cannot see because
Maybe you have disconnected, so that the old chat window has got disabled. So the Pooja is asking that stars plus gas plus dark matter is equal to what?
okay. Can she hear me?
Pooja, can you just raise your hand? I guess she left. There is another question from the Nisha,
Okay.
but I think so she's also left.
Okay, someone says that my mic is not working. Arjun gone. Who is this?
We can hear you properly.
Okay, I see this question
So
should be
let's
asked.
see. We can.
Okay, is that what you typed? Yes. It is said that the spiral galaxy have a different appearance when viewed from sideways, from where it looks apparently elliptical. Then how can we distinguish spiral and elliptical galaxy? My doubt is whether these elliptical galaxies are actually spiral, because we can only get a chance to view it sideways. Okay, but Santosh, is there a way I can talk? Because like, do I know that they are around?
Just wait. I guess Nisha is not around.
Okay, so can we get who is the next person? Can they ask
So
like?
next person is Jaswant. So I'm just unmuting the Jaswant.
Okay.
Yeah, go ahead. Jaswant, can you hear me?
Yes. Can
Yeah,
you
just
hear
go.
me back?
Yes, I can hear you. It's a bit faint, but
Yes, please. So, what can we say about?
evolution of galaxies from color magnitude plot. Is that what your question?
Yes, please.
Yes, I think I tried to like touch that upon, but so what I said is that in that plot, the blue, there is the galaxy segregate into two major part. One is the like blue cloud, and another is the red sequence. Okay, the red sequence is dominated by the more or less the early type galaxy, which means the elliptical is more evolved galaxy. In other words, okay, the spiral galaxies are in the blue cloud, so they are like more blue. So what? So is there a evolution? Of course, there is a sense of evolution here, because suppose the spiral galaxies which are blue, blue means the it's like the young stars. Okay, if there is no other complication. Okay, but like to get it straight, the blue means young, so and red is like no more older stars. So one way to think is that the galaxy go from blue cloud to red cloud, and when the young stars like are no more there, which means that if a spiral galaxy has like the blue color, and then which means they are like young stars, maybe they are forming stars. If we shut down the star formation, then eventually this like the stars will like not be anymore young, so they will evolve, and then they will be like sort of redder. So in that sense, there is evolution. Did you hear? Hello?
Yeah. So
Hello?
hello.
Yes,
Yeah.
yes, Santosh.
Yeah. So there is a next question from the Preet. I'm just unmuting Preet.
Okay.
Preet, can you hear us? Hello.
Hello.
Yeah, go on.
Hello.
Yes.
So good morning.
Morning.
Sir, why do galaxies exhibit different shapes? What factors are responsible for that?
Different shapes. Shapes means like elliptical versus spiral, or what is that your question?
Yeah, sir. Elliptical versus spiral.
Like elliptical have a different shape than the spiral. Is that the question?
Yes, sir.
Okay. There are two things. The elliptical galaxies are in general like the ellipsoidal sort of you can say that they are more or like a spheroidal shape. Spheroidal in a sense, I'm not totally saying the sphere, but there are galaxies which are totally round, and then there are sort of flattened in the like senses from the like one of the like axis of the rotation. So it's like a oblate shape, for example. Okay, so if you look in the sky, they would look like a more like an elongated ellipses. Okay, and then the spiral galaxies on the other hand are not rounded definitely. They are like more flat, like a disk. Now the question is like the what gives this like the
Certainly, the chances from the like one of the like axis of the rotation.
sorry,
Oblate shape, for example. Okay.
oblate shape.
The sky they would look like a more like elongated ellipses. Okay.
Yes,
And the spiral galaxies on the other hand,
it's like a rounder, or like if you look at an edge on, they will know it's like a very needle like. Okay, so if you want to know what gives you the like sort of like the shape, so one has to like the understand the fact there are two things. The spiral galaxies are supported by rotation. So most of the stars are like, to a good approximation, are rotating on a circular orbit. Okay, so there is not much of a stars are going on the random orbits. So the in elliptical galaxy on the other hand, the stars are not supported by the systematic motion or the rotational motion, but it's mostly like random orbits. I cannot draw you right now, but the orbits are like going on a three-dimensional space. Where at the spiral galaxy, the stars are like confined to a like the 2D plane. Okay, so this is to give you that's kind of like the way to like understand like sort of shape of a galaxy. Okay, so if you look at a spheroidal shape or oblate shape, which means that there are stars which are going on to like the all three-dimensional random orbits, versus the spiral galaxy that have mostly dominated by the rotation, and that's kind of sort of like gives you an explanation or for the why we see these kind of shapes. Okay, one is very flat like a disc like, another is rounded. Okay.
Okay, sir. Thank you, sir.
Hello, Kanak.
Yeah.
I guess we are running out of time because we have the next lecture. So
Okay.
I think so we have to stop over here.
Sure.
Yeah.
Okay, I don't know. So generally these questions like which comes, so they are like they are on the chat window.
Yeah. So basically, the who is giving the talk or the coordinator of that meeting will take up this question from this chat window and circulate to the speaker.
Okay. Anyway, you can say like if they